Okay, hello, assalamu alaikum. We are back and we are discussing forces on systems. Hopefully, you can hear me clearly. I've got the microphone attached to me today. That might help. Um, okay, so this is a follow through from what we've been doing about forces, Newton's laws, and all of that stuff. Today, we're going to be carrying through and talking about forces on systems, and this entails analyzing forces on systems, predicting motions, determining determining how the systems are interacting with each other. It's not difficult. It just requires that you pay attention. Okay, let's have a look. All right, so forces on systems. What is forces on systems? What are you talking about here? Remember how we talk about forces acting on a box? So for example, here's a table and here is a box, and there is a force of weight force acting downwards due to gravity, and we've got a normal force acting upwards. This is a reaction force from the table. This is acting on one object. The moment we do this, then it becomes a multiple object problem, or what we call a system, right? Where multiple objects are involved, and we can have another box over here, and then we can have a push force over here. And turns out that in physics, we can actually determine what is happening and how is each box affected and what are the forces acting on each box based on their mass, the acceleration, or the force. Okay, so that's basically what we're talking about over here. So the way we do it is we treat multiple objects as one system for easier analysis, and that way we can find the acceleration, for example, if we know the force, or if we don't know the force, we can find the force using the acceleration. The internal forces within the system cancel out. So if you imagine, for example, that you are walking down the aisle of a plane, does that really affect the plane or the way the plane is moving or its final destination? No, it doesn't, because that is an internal force. So internal forces don't affect the external force on the system. Use Newton's second law to predict motion of the system. Yes, we'll be using a lot of Newton's second law, which is force equals mass times acceleration. So hopefully you're familiar with Newton's three laws, being the law of inertia, the law of mass and acceleration, force, mass, and acceleration, and of course the law of equal and opposite reactions. That is another one that we'll be using quite a bit of. Based on how you have modeled systems with single objects, how do you think you might be able to model systems with multiple objects? Exactly the same way. Exactly the same way. So we draw a free body diagram, we show all the forces acting on the object, and then we add them together, work out the net forces. So much easier if I just show you. Okay, so you'll see how that works. Okay, so here's an example. Forces acting on systems. We've got a person pushing multiple boxes, obviously. Can we determine the forces acting on individual boxes? Of course we can, as long as we know certain data. Right, so what is happening here? We've got a person pushing a box, and this box is pushing another box. That's what's happening here. So we've got a person pushing a box, and then the box is pushing another box, and that's it. So, oops, sorry, just having problems with my setup this morning. Here we go. So that is an example of a system, right? We've got multiple boxes, and the way I would draw this body diagram is I would draw, oops, what's happening here? Is I would draw a dot for A, a dot for B, and there's no C. And so I would have the applied force. The applied force could be the push from the hand or foot or a pull or tension. It doesn't matter as long as it's the applied force, the force being applied to the system. So I've got the push force. So that is the applied force, and that's going to be push force of hand being applied. So the applied force by the hand on A, and then of course A is pushing on B, and we're going to call that force of A on B. And of course B is pushing back on A, because for every action there is an equal and opposite reaction. So that's going to be force of B on A. Now, what do you notice about those two forces, that one and that one? What do you notice about them? They're going to be equal, but they're going to be opposite. So one is going that way and the other one's going that way. One is going to be positive, the other one's going to be negative. Right. Question 59 says, imagine a third block, C, is placed to the right of block B. Okay. And can you easily draw a free body diagram for a system that includes blocks A and B and not B? A and C and not B? No. Ignoring block B leaves out important forces between A and C. Okay, so it's going to be, look, it's interactive. We're talking about contact forces here. We're talking about forces that are in touch with each other. This keeps going down for some reason. It is just not a good system I'm having at the moment. So I need to show the interactions between the two boxes. If I remove the box, it's not going to be very easy to show those forces. Okay, once again, it's just so much easier if I show you when we're doing the problems and the examples. Question 60 says, what type of force is FAB? What effect might the larger magnitude? Okay. So the force of FAB, so which one's FAB? That one. So that is the force that A exerts on B. So if we have the two boxes, basically what they're saying is you push the box, and then this box here, box A, is pushing box B. That's the force they're talking about. What kind of force is FAB? It is the force that A exerts on B, or basically the box, when box A pushes box B. That's what that is. It's a push force. It's a contact force. It is a touching force. It's a contact force between A and B, and that is the force specifically. It's when A is pushing on B. And what happens, what might be the effect if we have a larger magnitude of FAB? What have on if the two boxes, are made of thin cardboard? Well, if FAB is too high, then it might crush the cardboard box, because if the box is unable to withstand the push from box A, then it's going to crush it. That's the effect. Okay, moving on. Internal and external forces. External forces change system motion. Internal forces cancel out, so they don't really matter. Internal forces don't change the system motion. Internal forces follow Newton's third law, action-reaction. System acceleration depends only on external forces. Okay, so let's see what this means in practical terms. So here we have a system, and we've got three boxes, and there is an external force acting on it. The external force is the force coming from the hand. So we've got F hand, and it's an applied force, and turns out it's 13 newtons. I can see that from here. But anyway, so that is acting on A, and of course A is acting on B, excuse me. So A is acting on B, and then B is acting on C. So we have a force of A acting on B. We've got a force of B acting on C. Any other forces? Of course, we have equal and opposite reactions coming the other way. We've got a force of C acting on B, and we've got a force of B acting on A. Now, this and this are the same size. They are just equal and opposite. And this are the same size. They are just simply equal and opposite. Now, so let's say, for example, if I was to work out the net force on the system, what I need is the net force, all the forces on the system. So what do I have? I've got the applied force by the hand plus FAB minus FBA plus, which is that one, plus FBC. Why am I plussing some of them and minusing some others? It's because direction, right? So minus FCB. And what you'll notice is that AB and BA are the same, but they are opposite. So if I'm subtracting them, basically they're just going to cancel out. And these ones are gone as well. So what are we left with? We're left with the F net, or the net force acting on the system, is going to be the external force, which is what we already knew, which is going to be the push of the hand. And that is what this means. The external force changed the system motion. Everything else cancels out. They just cancel out. There's an equal and opposite reaction. So they cancel out. Internal forces, action, reaction, and system acceleration depends only on external forces. Okay, 61. We can actually do 61. Using the figure of the three blocks, determine the internal force block C exerts on B. So we want to know the internal force that block C, which is this guy here, exerts on this guy here, block B. Well, I want you to think about this logically. If I'm pushing something, okay, if I'm pushing something and it's got, I'm going to try and fix my table while I'm talking to you. I've got a screw and I've got a screwdriver, well, a drill screwdriver. So I'm going to try and do this so it doesn't happen again because it's annoying me. But sorry, as I was saying, I want you to imagine, oops, that's a bit louder than I thought it was going to be. Excuse me. Okay. As I say that, hopefully that won't flick anymore. Right, so I want you to imagine yourself pushing something small. Okay, like let's say, for example, you're pushing a rabbit or a bunny, right? There's going to be a pushback on you. The way you push on them, there's going to be a pushback on you. But it's going to be small, right? Now, I want you to imagine pushing an elephant. Now, that's going to be a different case, right? So try to imagine what's going on here. There's box A pushing on box B, which is pushing on box C. There is a pushback from box C on box B, right? So what is going to be the influencing factor is going to be the mass of box C. So if I'm trying to determine the force that block C exerts on B, I'm trying to determine the force of block C exerting on block B, I'm looking for FCB. That's what I'm looking for, the force that C exerts on B. And the way I work that out is it's going to be like this. FCB is going to be equal to the mass of C multiplied by the acceleration. Okay? That's it. Why only the mass of C? Because that's the only thing that they asked for. First of all, they asked for FCB. And the only thing that influences FCB is the mass of box C. And if there was no box there, there wouldn't be FCB, right? Or if the box was heavier, then that FCB value would be greater. So that's why it's only box C and the mass of box C that influences the outcome in this stage. So it's going to be whatever that box is, 10 kilograms multiplied by the acceleration, which I believe they've given to us, which is 1 meter per second squared. And so it's going to be 10 newtons. But just be careful with the signage. So it's going to be 10 newtons to the left, or if you prefer, it is negative 10 newtons. That is going to be the answer. Question 62 asks, a force is applied on a system consisting of a flatbed truck and a car, causing an acceleration. One of your classmates makes the claim that the larger flatbed truck experiences a larger net force than the smaller car on the truck. Use the evidence to argue for or against the claim. Yes, I agree. The larger truck, the much heavier truck, experiences a larger force. Well, because Newton's second law states that force equals mass times acceleration. So although they are both together, the force that is experienced by the truck having a much larger mass is going to be much greater than the small car. And if you're having a bit of a problem understanding this, I want you to imagine yourself, right? You're moving along, you're going along, you're running, for example, And let's say a mosquito is hitching a ride on you. So a mosquito lands on your shoulder, and as you're running along, you don't notice the mosquito. Now, are you both experiencing the same force? Of course not. So the forces you're experiencing are different based on the mass, right? So you might have the same acceleration because you're both kind of riding together, but based on the mass, and since the truck has more mass in this case, it needs more force to accelerate. But yeah, but you both experience the same acceleration. Right. Let's move on. Oh, it's time to do some problems. Very good. I think you'll understand this a lot better if you get a pad and paper and actually start drawing and doing the problems yourself. It'll make much more sense. Okay, let's have a look. There is a push force acting on the 3 boxes. It is 40 newtons. All the boxes are the same mass. Ignore the friction. Okay, we're asked to do 2 things. Draw the free body diagram and determine the force of box C exerts on B. Okay, so that's very similar to the example we saw before. So first of all, the force of the system, of the entire system, is going to be 40 newtons. So that's the F net is going to be 40 newtons. Now the first thing I need to do is determine the acceleration. So that's step 1, okay? Well, actually, step 1 is draw the free body diagram. So I'm going to do that first, and then I can work on everything else. So I've got A, B, C. What are the forces? I've got a push force here, which I'm going to call F push, and that of course is the applied force. I've got a force that A exerts on B. I've got a force that B exerts on C, and likewise I've got a reaction force that C exerts on B, and I've got a reaction force from B on A. And that's it. That's all the forces I have. Right, so what are we being asked to do again? Determine the force of box B exerts on B. Oh, C exerts on B. So there are different ways of doing this. I guess what you can do is, first of all, step 1, you have to determine the acceleration. And the way I would do that is by looking at the net force. So the net force on the system is going to be 40, while the mass of the entire system is going to be 6 kilograms, and that's because each one of those is 2 kilograms. Even though they're different sizes, they have the same mass. So 2 kilograms each, a total of 6 kilograms. And so the acceleration is going to be the net force over the total mass. And the way we write that is m total. And that's going to equal 40 divided by 6, which is 6.7 meters per second squared. So this is in fact step 2, because step 1 was to draw the free body diagram. I want you to remember step 1 is always to draw the free body diagram. Step 2 is to work out the acceleration. And now step 3 is to look what the question is asking for. So the question is asking for force C exerts on B. So that's this one here. And the way I would work that out is by finding the mass of C. So FCB is going to equal the mass of box C multiplied by the acceleration. So that's going to be 2 kilograms multiplied by 6.7 meters per second squared, which is equal to 13.3 newtons. Okay, that is the size of the force. Now, if I work that out, now of course it's going to be negative because it's going to be facing the other way, as you can see, right? Now, if I work that out, then I've also worked that out. Okay, so I'm just going to change the color for a second. So that's negative 13.3, and guess what? That's going to be 13.3, just like that. Now, what's going to be the force of A on B then? And somebody might be asking, well, hang on a minute. And what's the force of B on A? Well, slightly different situation here. So here's the deal. If I'm trying to work out the force of B is applying on A, like let's say for example this one here, then what am I going to do? This time I'm going to try and use both B and C to calculate the force. Why is that? Because I'm looking for this force here, right? I'm looking for this force here, right here at the barrier between that B is exerting on A. But you see, B is not just B. B has got C attached to it. So it's going to be those two together pushing against A. So in reality, the force of, if I'm calculating this one here, BA is going to be MB plus MC all multiplied by A, which is going to be 4 multiplied by 6.7, and that's going to equal 26.7 newtons. And of course, because it's facing the other way, it's going to be a negative. So that's going to be negative 26.7, while that's going to be 26.7. Okay, so we've got a push force of 40 newtons to begin with, okay, which results in box A pushing box B with a force of 26.7 newtons, and likewise box B pushing back on box A with a force of 26.7. Box B is going to be pushing box C with a force of 13.3 newtons, while box C is going to be pushing back on box B with a force of 13.3 newtons in the opposite direction. Okay, hopefully that wasn't too hard. What you need to do is, first of all, draw the free body diagram, determine which forces are acting on which parts or which objects, find the acceleration, and then work out the individual internal forces. Okay, let's look at the next example. In this example, we've got two boxes that are of different masses. So I've got a push force, once again, 100 newtons acting this way. And then I've got this box here, which is 10 kilograms, and this box here, which is 5 kilograms. And once again, we ignore friction. Okay, draw the free body diagram. So step one. Step one. A, and this is B. I've got a push force, which I'm going to call F push. You can also call it F applied force. And I've got the force of A acting on B, and I've got the force of B acting on A. And that's it. That's all the forces that I have. So, first of all, the net force, the total net force, is going to equal the external force, which is just the push force, right? And I can prove it to you once again. It's going to be F push plus FAB minus FBA. And we know those two are pretty much the same because they're equal and opposite. And so it's going to be F net is equal to F push, right? So I know that, and that's going to be 100 newtons because it tells us. Now, what am I trying to work out? Remember, I'm trying to work out the acceleration. Maybe I should move this slightly. I'm trying to work out the acceleration. So it's going to be, remember this formula here? The formula states that force equals mass times acceleration. And so if I'm trying to work out the acceleration, it's going to be F net over mass total, which is going to be 100 newtons divided by total mass, which is 15 kilograms. And that's going to be 6.7 meters per second squared, right? I think that's the same as the previous question. So I've got the acceleration, and then I'm being asked to determine the force of A exerts, that box A exerts on B. Okay, so let's look at box A. I want you to look at box A for a second, and that's box A right here. What are the forces acting on box A? Okay, so I've got basically the forces acting on box A is going to be the total forces F net acting on A is going to be the push force F push minus that. And those are the only forces acting on box A. Remember, we're not looking at the forces acting on anything else. We're just looking at the forces acting on box A. So it's going to be that minus FBA. So it's going to be 100 equals, oh no, sorry, F net equals 100 minus FBA. Now, how do I determine FBA? Well, I know what the mass of B is. It's going to be 5 kilograms, and I know what the acceleration is, which is 6.7. So I can work it out. So it's going to be times 6.7, which is acceleration. So it's going 5, sorry, let me just do this properly, times A. So it's going to be 5 kilograms multiplied by 6.7. So that's going to give me 100 minus, it should be about 67. 67 times, okay, so it's about 67 newtons. That's it. That's the answer of net force on, oh no, sorry, that's the net force on box A. That's not the answer, that's the answer of, that's the, so that's 100 minus that, which is 67. Okay, so what I've just worked out was the net force on A, but I also know that FBA is equal to, I've just worked it out, 5 times 6.7, that's 33.5, 33 point, I think that's supposed to be 33.3 newtons, and so likewise that's 33.3 newtons, okay? Because remember, it's the mass multiplied by the acceleration, so I've just worked that out. So it's going to be 33.3. And I've also worked out the net force on box A. The net force on box A is going to be equal to the push minus this force here. Yeah, and so the net force on, yeah, so that's it. Okay, what they're asking for was this thing here, which we've worked out. Okay. Okay. Let's keep going. What about box? What if we've got them stacked up? So here we've got a system where the boxes are stacked up on top of each other. Box A is 2 kilograms, box B is 5 kilograms, and box C is 11 kilograms. We got to draw the free body diagrams for all 3 boxes and determine the force of A on B and determine the force of B on C. Okay. Right. The way I would do this, obviously, you should know by now, is first of all, we draw the free body diagrams. So first thing is, here's A, here's B, and here's C. Let me change the color. So what are the forces acting on A? We've got the weight force of A and the normal force of actually the normal force, which is going to be B, is going to be applying on A, right? So we've got the weight force of A and we've got the normal force which B is applying on A. So that's how we do this. We say BA. So we've got the force of BA, and that's the normal force. What else have we got? We've got box B, and what are the forces acting on box B? We've got the weight force of B. We've also got the reaction force or the normal force that box C is applying on B, we've also got the force that box A on top is applying on B. Okay, so we've got two different forces here. Oh, sorry, A applying on B. Okay, now what about box C? Once again, we've got the reaction force or the normal force, but this time it's going to be from the table, right? So assuming this is a table, for example, so we've got the table is applying a force upwards, and we've got the weight of C, so that's force of weight, plus we've got the force of B, box B is pushing down on C as well, so that's going to be force of B on C. Okay, so that's the hard part. The hard part is done. We've determined all the different forces acting on different objects. Remember, it's about interactions. So the two boxes are touching each other. That means they're interacting with each other. What I've just said was box A is has got a weight force acting down, and then box B is pushing back up, right? Whilst box B, because it's in the middle there, it's got the weight force that it has. Okay, it's got its own weight. It's got the reaction force from C, but it also has this push down force from A, because A is on top of it. Now, A didn't have a push force coming down from anywhere because there's nothing on top of it, whereas B has its weight force, has its reaction force from C, as well as a push down force from A, right? And C is the same. C's got the normal force acting up from the table, and it's got its own weight force because it has a mass, right? So it's got a weight force, and then it's got the force of B acting down on it, right? Okay, so now that we've got that part, the hard part is definitely done now. Step 2, what do we got to find? Determine the force of A on B. Well, there's no acceleration in the horizontal direction whatsoever. Nothing's being pushed. So the acceleration in that regard is 0. But what I do have is I have weight, right? So I'm trying to determine, first of all, can I determine the weight force, FWA, the weight force of box A? I sure can, because I know that weight force is equal to mg. So that's going to be 2 kilograms multiplied by 9.8, 9.81 if you like, and that's going to be approximately 19.6 newtons, right? So I've just figured out this one here. So that's 19.6. Okay, now because I've figured that out, that reaction force up here is going to also be 19.6. And because I've figured that out, that's going to be 19.6 as well, because FAB is equal to FBA, right? So it becomes really easy. Once you figure one, you can figure out all the others. What about the weight of B? How can I determine the weight of B? Well, it's exactly the same. All I need to do is find the mass of B, which is given to me in the question. So it's 5 kilograms. And so it's 5 multiplied by 9.81. And so it's 49. So that's going to be 49 newtons. Of course, I should remember the newtons. So what about FCB? How do I know that? How do I figure that out? What's the force that C is exerting on B? Well, that's easy. All I have to do is add these two together. Why? Because remember that everything at the bottom has to equal everything at the top. These two have to equal. Like that has to equal this. In this case, it was just one force. So that's why it was easy. Whereas here, 1 is equal to 2, right? So I have to add those two together. So it's 49 plus 19.6, and that's going to equal 68.6 newtons. And once I know that, then I know that. That's going to be 68.6 newtons. What is the weight of box C? That's going to be 11 times 9.81. That's going to be 107.9. So I've got those two. What's that going to be? You guessed it. It's going to be these two added together, right? So that's going to be that plus 68.6, which is 176.5 newtons. Now, if I want to check, right, like let's just say I want to do a check. Because I've just determined the force of A on B, which is 19.6, and I've determined the force of B on C, which is 68.6. But let's say I want to check that my workout is correct. Well, there's one easy way to figure it out. If I add all the masses together, so it's going to be 2 plus 5 plus 11, that's going to give me 18 kilograms. Now, if I multiply 18 kilograms by the acceleration due to gravity, which is g, so multiplied by 9.81, that should give me 176.58. And that is the amount that I got here for the normal force exerted by the table on the boxes, right? So that checks out. That means my calculation is correct, okay? So that's one easy way to check if your calculation is correct. Next, I've got 3 identical boxes, 2 kilograms each, and the pull force is 30 newtons. So that pull force over here is 30 newtons. And so I'm asked to draw the free body diagram to begin with. So here we go. A, B, C. Okay. And I've got a tension force acting this way. T1. I've got a tension force acting this way. T2. And I've got the applied force, which is the pull force in this case, and that's 30 newtons. So that is the free body diagram essentially. Now I do have an equal and opposite tension force acting this way, and that's just T2. Now if you want to, if you prefer, I can write T2BC, and that's T2CB, which are the same. And this one is T1AB, and this one is T1BA. So those are the forces that are acting on the system here. That is T1 and that is T2. And they want me to determine the tension in each rope. Okay, so first of all, the tension over here is equal to the tension over here. They're exactly the same, so I just need to work out one of them. And that is equal to that, so I just need to work out one of them. How do I work it out? Remember, first of all, you draw the body diagram, you determine the forces. We've done that already. Easy. Next step, step 2, we gotta figure out the force equals mass times acceleration. And so we've got the total force, which is 30 newtons. We don't have the accelerations, but we do have the mass, which is m1 plus m2 plus m3, so that's 6 kilograms multiplied by acceleration, so it's going to be 6 kg multiplied by a, and therefore acceleration equals 5 meters per second squared. Once I have the acceleration, I can work out the rest of it. Easy peasy. Step 3, what do I need? I need to figure out, first of all, the tension of B on A or A on B. And the way I'll do that is by going F tension AB is going to equal the mass of A, the mass of A, which is 2 kilograms, because that's the only thing that's pulling on this rope here. So it's going to be 2 kilograms multiplied the acceleration, which is 5 meters per second squared, and that's going to be 10 newtons. Okay, so the tension in 1 is going to be 10 newtons. What about the tension in 2? Well, the tension in 2, which is BC, is going to equal the mass of this and this, because of course this rope here is pulling both of these. So it's going to be 4 kg multiplied by 5 meters per second squared, and that's going to be 20 newtons. Right? So that's 20 newtons, that's 10 newtons. The total force here is 30 newtons, which checks out, which is equal to this plus this. Easy. Okay? And that's that. So to summarize, treat the system as a single body to work out the acceleration using Newton's laws. Draw the free body diagram and calculate the net force acting on each component individually. Keep practicing, okay? It's not hard. You just need to practice. Once you practice, once you get the hang of it, it becomes super easy. Okay, good luck. Over and out.